In the last video, we looked at what the four fundamental spaces of the B matrix meant. Now let's take a look at a few examples. In fact, this assignment itself is just an elaborate example of the application of the four fundamental spaces. So let's look at the structure that's got four joints and three members, 4 degrees of freedom. So n is equal to 4, m is equal to 3. We see immediately that this structure is unstable. It cannot support any vertical loads. But let's deduce this formally using the four fundamental spaces. So first, let's determine the B matrix. So the B is the matrix that takes the joint displacements and produces changes in length. We remember this. So delta 1 is simply U1. So the first row is just 1, 0, 0, 0. Delta 2 is U3 minus U1. So it's minus 1, 0, 1, 0, and so on. Okay. And we see that the B matrix has two linearly independent columns. So the column space of B has dimension 2, or in other words, the rank of B is 2. So we can draw the four fundamental spaces of this B matrix. B takes R4 to R3. And we can partition R4 into the column space of B transpose and the null space of B, and R3 into the column space of B and the null space of B transpose. And these are perpendicular, as we've seen before. So the dimension of the column space of B is the rank of B, that's equal to 2, and the dimension of the null space of B transpose is then 3 minus 2, that's equal to 1. And we can construct a basis for the null space of B, and from which we deduce that the dimension of the null space of B is 2, dimension of the column space of B transposed is 4 minus 2 is equal to 2, and the null space of B transposed is 3 minus 2 is equal to 1. Now let's construct a basis for, let's understand what the four fundamental spaces mean by constructing bases for each of those spaces. So basis for the column space of B is 1 minus 1, 0, 0, 1 minus 1. We can see that the vector 1, 1, 1 cannot be written as a linear combination of these two vectors. So 1, 1, 1 is not a compatible deformation. Why is that? Because I cannot produce a change of length of 1 in each member without translating all the joints 1 unit, which I can't do because 4 is fixed. So we understand what the column space of B is. Now let's construct a null space for the, let's construct a basis for the null space of B. So by inspection 0, 1, 0, 0, 0, 0, 1, 0. And let's see what these displacements mean. We see that these displacements are mechanisms. So these are displacements that can occur in the structure without any resistance. Such displacements are called mechanisms. So we understand what the null space of B tells us. Now let's construct a basis for the null space of B transposed. Again, by inspection, a basis is just 1, 1, 1, 1. Now, if we set F1 equals 1, F2 equals 1, F3 equals 1, we see that this is a self-equilibrating configuration of internal forces. We call this a pre-stress mode. So if we pre-stress it in such a way that each of the forces are equal in all the members, that's self-equilibrating. Lastly, we look at a basis for the column space of B transposed. Again, by inspection, it's 1, 0, 0, 0, 0, 0, 1, 0. And these external forces are forces that cannot be resisted by the structure. So we understand formally, all these are kind of obvious just looking at the structure, but we understand formally how to infer these things from the four fundamental spaces. For a complicated structure, we can't just infer these things looking at the structure, as is the case with the structure of the assignment, the 3D truss. But the four fundamental spaces help us formally infer these things. So in all these examples, we constructed bases and deduced rank and so on simply by inspection. This is not always possible. So the MATLAB functions rank, null, and SVD can be used to compute the rank of a matrix and construct bases for the null space and column space of a matrix. Let's look at another example. In this case, we won't do detailed calculations, but we'll see just by intuition, just by observation, can we deduce some things. Okay, so how many elements in the null space of B? Or rather, what's the dimension of the null space of B? What's the dimension of the null space of B transpose? Let's take another example, a structure like this, which is kind of a construed structure, just to illustrate a point. So it's kind of a truss inside another truss. Again, what is the dimension of the null space of B? What's the dimension of the null space of B transpose? So what I encourage you to do is to pause the video and see if you can answer these questions by yourselves based on your understanding of what these null spaces mean. But I will write the answers now. The first structure is 3 rigid body mounts. So the null space of B is dimension 3. Degree of static indeterminacy is 1. So then the dimension of the null space of B transposed is 1. In the second structure, the object inside can freely rotate. There's one internal mechanism, so the dimension of the null space of B is 1. And the dimension of the null space of B transposed is 2 because the degree of static indeterminacy is 2. So these internal mechanisms are actually quite useful. And if we look at deployable structures, internal mechanisms are intentionally introduced so that the structure can be deployed, and then it's stabilized in the deployed configuration using pre-stress. This is done, for example, in the space structures in the International Space Station, and the paper that is attached to this assignment has some insights on this as well.